Hi everyone, welcome back to the series of tutorials on geostatistics. Here's our plan for today. In the first part of this video, I will be covering basic installation instructions for the Julia language, the IJulia kernel for running Jupyter notebooks, which will be the platform you'll be using in these tutorials, and the GeoStats.jl project. In the second part of this video, we'll be looking at an example notebook with two purposes. First, to illustrate how Julia code looks like in general, and second, to illustrate what's going to be the format of these upcoming tutorials in geostatistics. In the description of this video, I'll also be sharing the specific times for each of these sections, so that if you already know how to install Julia and the project, you can jump directly to the second section to see this example notebook. This example notebook will be on a simple least squares problem, and upcoming tutorials on geostatistics will start in the next video. So let's get it started. First, installation. To install the Julia language, we go to the JuliaLang website, julialang.org, and we go to the download button here. We'll see that there are many download options, and we'll always be looking at the current stable release, which is currently version 1.4.1. You will look at your operating system, in this case mine is Linux, and I'll click here to download the binary of the language. While this download is taking place, I would like to point out that these installation instructions will vary slightly depending on the operating system you have. So for instance, if you are on Windows, you will likely get a wizard that you can press next multiple times and get the language installed. If you are on Mac OS, you will get an image that you can double click and drag and drop to your applications folder. And the installation on Linux will be covering more details here. So after the archive is downloaded, you can open it and you see that there is a bin folder with your Julia executable. You can extract this folder somewhere in your system, the entire folder, but since I've already done that, I'll just skip this step. So you can go to your file system where you downloaded Julia, and you can see that there's the same bin folder here. And right now I can just, for example, right click and ask to run in the console. And as you can see, this is the Julia prompt telling you the version 1.4.1. Additionally, and that's an additional step for users in Linux and Mac, we would like to run Julia from the terminal from any folder in the system. To do this, we need to create a symbolic link that points to this executable that's saved in an arbitrary folder that I just created on my desktop, and I have to link this executable to the path in the system. So what I will do, I will open a normal terminal here. Let me increase the font, and I have to find out what are the folders that I can create this link. So you can type echo $path, and this will show you the folders you can use to create links so that the operating system can see the Julia executable. In this case, I'll be using user local bin because I know this folder is empty. And what I will do then is create this command here, ln-s for symbolic link. I'll provide as the first argument the path to this executable that I have just downloaded. It's in my home folder, the desktop, Julia, bin, Julia. And in the second argument, I'll be providing the name of the link. So user local bin, and I'll call it Julia as well. I need privileges to write on this folder, so I'll write this command with the sudo. And now you can run Julia from anywhere on your system. This completes the installation of Julia on Linux. The next step would be the installation of the IJulia kernel. So unlike other languages such as Python that require additional programs to install packages like pip and conda, Julia comes with a fully featured package manager built in. To access this package manager, you can press right bracket like I'm pressing here in the terminal, but you press it as the first character in the line. So if I press here, I switch to package manager mode. There are many commands that you can type. You can press help to get the help of all the possible commands in the package manager, but in particular we'll be using the command add to add packages. So you can type help add, for example, and it will tell you what the add command does. Because I don't want to compromise my existing installation of packages in my computer, I will create a temporary folder to install these packages. So I will open a separate terminal here in the left. I'll move this here to the right and increase the font again. I'll create this temporary directory in this folder. So just to be clear, you don't need to do this in your machine. I'm just doing this to not compromise my own installation. And then I'll export this depot path variable and point it to this just created folder on my temp folder. So now if I start Julia from here and enter in package mode again by pressing right bracket, I can type status to see that I have an empty environment because I'm on this temporary folder. You can go ahead and type add IJulia with capital I and capital J, and you'll see that the first thing it does is clone this repository called the general registry that contains the list of all existing registered packages in Julia, in the general registry, of course. And after it clones the repository, it will look up the name IJulia and install this package automatically. So it's installing all the dependencies of the package and building some of the dependencies like Conda and IJulia. Now you can exit the package manager mode by pressing backspace. And now you're back to the normal Julia prompt. And you can load the package, that is, using IJulia. The first time you load a package, like using in the name of the package, as you do in Python with, for example, import, this package will get pre-compiled, as it's shown here in this message. Now, the next step is to type notebook and press enter. This will try to start the Jupyter notebook. Because this is the first time that I'm installing IJulia in this temporary directory here, it will ask if I want to install Jupyter via Conda, and you can just press yes or just enter. This will download a mini Conda installer inside of the Julia folder, and if you already have Jupyter in your system, it will automatically detect the existing Jupyter and you will not need to install a separate mini Conda here. But while it's downloaded a mini Conda, I would like to invite you to check the Julia website again for some resources. It's going to download all the dependencies and this may take some time. After it's done, it will automatically open a tab on our browser, so we will know when it's done. So going back to the browser and going to the website again, I invite you to check some tabs here, for example, the documentation tab and the learning tab. The community tab is also very important. In the documentation tab, I really think it's a good idea to read the manual at least. And if you have some experience in other programming languages, maybe these sections here on differences from other languages can be helpful. So it compares, if you come, for example, from MATLAB, what you should expect in terms of the main differences from what you're used to. After you read this manual and you get an idea of how Julia works, you can go to these other tabs here, learning resources that have a bunch of resources like videos and books and so on. And the community tab has some links as well for chats like Slack and other chats like Zulip, which are listed in other places on the Julia community, like here. And you can see that the IJulia installation has finished, because as you've noticed, there was this new tab that was open here automatically. And you can see that you actually can create Julia notebooks. If you go here to new, I don't know if it's too small. So if you click new, you see that there's an option now to create a Julia notebook. And that's all that's needed to install IJulia. I'll close it here for now, because we will not be using it. And now we're going to go to the third step of the installation, which is installing the GeoStats.jl project. I'll close the Jupyter that was just launched. Let me clean this terminal as well. And now I'll do the same. I'll go to package mode by pressing right bracket and then add GeoStats. As it did with IJulia, it will install the package and its dependencies. And after it's done with this dependency installation, we can simply try to load the package again with using GeoStats. And this command will, as it was the case with the IJulia package, will precompile the GeoStats project, because that's the first time we are loading it. So it should be almost there. Okay, now we can go backspace, go back to the normal Julia mode and type using GeoStats. It may take some time, but that's all that's needed to conclude the first section here of this tutorial on installation of Julia, the IJulia, and the GeoStats.jl project. The second part is exemplifying how Julia code looks like in general and the format of these notebooks that you'll be using. Let's see if this pre-compilation is done so that we can check that we can use some of the objects from the project. It's going to take a lot of time because that's the first package ever we installed in this environment. So you see there's a bunch of dependencies that came directly and indirectly, and they all need to be precompiled before the project is precompiled. Meanwhile, I will just go to this other terminal here, which is my normal Julia environment. And I'll do using package, I'll load Julia again, of course, using the package manager, and I will just rebuild the IJulia because I've created a temporary folder and I'm not sure if it changed some of the links to point there instead of pointing to my normal IJulia configuration. So I'll just hit this guy here while it's building, okay? And I can then, using IJulia, and launch my notebook. Before launching, I noticed that it finished here, so we can check, for example, that you can create a regular grid with float 64 coordinates of 100, 100 points, for example. And that's one of the types that's defined in the GeoStats project. Okay, so the installation is concluded. I can close this now, and we can concentrate our attention to the second part of the tutorial. Here, I'll be using IJulia and launching the notebooks again. So this time there's no need to install anything. And here is an example notebook that I created on this folder tutorial. And by clicking this notebook, that's what we get. So I hope that it's easy to read. This tutorial here and all the tutorials that are upcoming in this series of tutorials on geostatistics will try to follow the same format. In the first cell, which is this first cell here, what I'm doing is I'm loading the package manager and I'm instantiating an environment that's in that folder. This is to make sure that all the versions of the packages and dependencies that I'm using are the same that you will be using. This additional command here, precompile, tells that if that's the first time ever you're running this environment, it will precompile, or it will try to precompile all the packages in that environment so that you don't waste time precompiling packages in the middle of your notebook. So I can execute the cell by pressing Ctrl Enter, for example, and it's already done because there's nothing to precompile. This environment was already precompiled. The second cell of these tutorials will often have this random seed here set to a fixed integer, for example. And this is to make sure that if anything we run depends on some random numbers, we can reproduce the results. So that's the second cell. Then we start our example notebook. Here's an example notebook on least squares problem. It's not an example again on geostatistics, but just an idea of how we'll be doing this. We come with a title of the example, the problem we'll be addressing, and we'll be right away defining what the problem is. So here we are considering that there exists a function, a linear function, and we have at least a few observations of this function of the form x1, y1, x2, y2, xn, in. We say that these observations are noisy with some normal noise here, and we state the problem to be learn the function f, or the parameters of the function f, based on the dataset. Then we'll be also providing some code initially so that we can see this problem in code, right? So this package here, the getFly package, is the equivalent of the ggplot2 package from R for plotting. And it's based on this idea of grammar of graphics. So here I'm defining the function that I've stated in the problem. It's a linear function with unknown coefficients, 3 and 1. I create some data for this function. N is 100 observations. I create the axis to be a range from 0 to 1 with length n. And I create a vector y, which is evaluating this scalar function on every entry of this vector x, and adding some Gaussian noise run n of length n. I then zip this vector x with vector y into a data set. And finally, I can plot one layer with the scatter plot and another layer with the true function. You notice that it took a while to run, and that was again loading the getFly package. I can execute again, and it should be executing a bit faster, right? So that's the data set we'll be using, and you can interact with this, and if you hover your mouse over this question mark, you'll see the options for interacting with this plot. Then we will be proposing solutions, right? So after we state the problem, we start proposing alternative solutions. One solution to this specific problem, for example, could be the analytical solution to the least square problem, which is closed form. So what we do, we write this matrix, boldface x, which places all the x's in the first column and a bunch of ones in the second column. We create this boldface y, which just repeats the y's we have in our observations, and we put the parameters to be learned, a and b, in a vector theta. We then minimize this squared error here, which is the square error between the observed y's and the model on thetas we defined, plus some regularization term here, which is lambda times the square norm of the parameters, where lambda here is known in the literature as the Tikhonov regularization parameter. So there is a closed form solution to this problem, which is given by this expression. We don't need to go into the details of why this is. And then if you find this optimal theta, which is this theta hat, by minimizing over the values of theta, you can then create the approximation of f as this g of lambda x as simply the product of this augmented x with 1, with this vector theta hat. So how this looks like in Julia code, right? So one of the nicest things about the language is that's very convenient to write code that looks like linear algebra like this. So I can do using linear algebra, which is a standard library again, and I can start defining my objects as I did here. So I first define my X matrix. I can say X or even backslash boldface X to create this matrix, and I press tab to complete the Unicode. And I'll define it to be a matrix where the first column is the X and the second column, so the column here is denoted by a space, is ones of length n. So that creates my matrix X, and I'll similarly create my matrix boldface Y, which is simply a copy of my normal Y. After I have X and Y, I can define my solution, which is expressed in terms of X, Y, and lambda and the identity. One thing that you will notice is that Julia has an identity, which is a smart identity. If I press here I, you see uniform scaling. So this is just acting like the identity for matrices. It doesn't store any memory. But if you need to actually create a matrix of a given size, you can say identity tree, for example, to create a diagonal identity. This I replaces the I function that you see in MATLAB, for example, when you say identity. So here's our solution. We can say backslash boldface theta. It's a function of lambda, so backslash lambda tab is equal to open parenthesis backslash x transpose times backslash x plus lambda I, and then you can back solve back and then transpose y. So this defines a function as a function of lambda, right? So I can, for example, call a lambda equals 1 or something, and it will always solve the system and produce the theta, which is a and b for a given lambda. If I, for example, save lambda equals 0, that's the regularization equals to 0, so I'm solving the original least square problem without regularization. And you see already that the parameters a and b are approximately 3 and 1, which were the unknown parameters we had set here in the beginning. So now we can construct the solution. So I'll say it's a g of x, where I optionally pass the lambda. It's going to be the augmented x dot product c dot, like in LaTeX, and then boldface theta of lambda. So this creates a function, and I can, for example, plot the function f, the original, the approximation g from 0 to 1, for example. And here you see that indeed, let me give it also some labels. I can say that the color is f and g. So you can hide the g, so that's the true function, and we learned the function g, which is pretty close. I can also give some title so that we keep that as the Tikhnov, how do I write this? Tikhonov solution. So that's the solution. Now we can move, for example, to another solution. So we'll be having another section of Markdown, and we can always edit this text here by pressing the cell, and you see the original Markdown behind this cell. You can press again Control Enter to come back to the normal visualization, and that's defining a different solution. So this time we will be solving the same problem of least squares by minimizing this sum of the loss, which is the empirical risk over this data set. And we'll be doing this by, for example, gradient descent. So how it works, we initialize these parameters to some random value from some Gaussian, for example, and then we descend the negative gradient. So we update this data vector from the previous by subtracting the gradient at the previous with some learning rate alpha. And we do this for some number of iterations, d1 through m. So how we would write this in Julia, right? So the first thing we will do is load this package in Julia called Flux, which is the package for automatic differentiation and more generally neural networks in Julia. It would be somewhat the equivalent of PyTorch, but with some advantages. So you load the package and now you start defining the objects, right? So you can call this function age that I defined there, the hypothesis function, as age of x and theta. And you press tab again to make it exactly like the LaTeX. And the function is going to be what? It's going to be the first parameter theta times x plus the second parameter of theta. So that defines the function. I can define my loss to be script loss like in LaTeX, x, y, and theta. And this loss is going to be the square loss. So I can say age of x theta minus the y squared. Given the loss, I can define my objective function, which is the empirical risk. So I define my empirical risk for the parameters as the sum over, now I have to sum over the data set for aggregating all the losses, right? So I calculate the loss of x, y, theta for x and y in my data set, which is script D. I define it in the top of this notebook. This is the sum of the losses over the data set, and I can divide by the length of the data set to get the mean. So you can see that I can evaluate this objective function, for example, at the parameter 0, 0. And you see that it's minimized, for example, when it reaches the true, right? The 3, 1, if I remember correctly. Now we want to do gradient descent. So there are many ways you can approximate the gradient of a function. Here we'll be using Flux to approximate this gradient automatically. So here, that's the gradient function from Flux. You can say gradient of this objective at a specific point. So you can say, give me the gradient at the point 0, 0, which is the theta equals 0, 0, right? So what Flux will do is to get this Julia code here. It will differentiate this code, and you will calculate the gradient and evaluate it at the point theta equals 0, 0. The first time it takes some time because it's compiling this gradient for the function, but if you execute it again, you see that this is the gradient. It returns the gradient as a tuple for every parameter. So there's only one parameter here, theta, and so that's the tuple with a single parameter. I can then get this first entry of the tuple to return the actual gradient. I'll generalize this and I'll write the gradient function, which is nabla j of theta equals the gradient of j at theta. And now I define this general function to compute the gradient, right? So I can see that, for example, nabla of j at the true optimal, which is again 3, 1, should be approximately 0, right? Because there is the gradient vanishes there. So now let's perform our gradient descent. I'll create a function, descend, which takes some maximum number of iterations and optionally a learning rate that I'll call here alpha, as in the code there. I will then start my theta at random, which is this initial step. Theta equals ran2. I'll loop for t in 1 to m. And what I will do, I'll just update my theta to be minus equal my learning rate times my nabla j of theta. I end the loop and I return the theta. So in Julia, the return is implicit. You can explicitly add return here, but it's usually not needed. You only use return when you want to return prematurely, for example, before the last line of the function. So if I call this descent function for some, let's say, 1,000 iterations, it should return my optimal theta, which is again close to 3 and 1. Let's save this data on a data variable, and I'll create a new function here, key of x, which is again x augmented c dot of my theta. So here I can plot again my true function f and my approximation q from 0 to 1. I'll right away give it a title, which is going to be the gradient descent solution. And you should see that it's again an approximation that's pretty close to the true function f. One of the nicest things about Flux, which I mentioned, it has some benefits over PyTorch. I'll clarify what I meant now. And the difference here is that Flux takes gradients of arbitrary Julia code. So, for example, the first thing I'll show here is how it can intercept the compiler and create very efficient code at the assembly level, right? So if I define a function p of x, which is 2x plus 1, for example, if I say, give me the gradient of p at x equals 1, for example, you know that the gradient is 2 regardless of the value of x. So if I do this, I get the gradient of 2. But more than that, if you actually check the assembly code, in Julia there is this command, code native, that you can prepend to a command, and you see the assembly code that's being generated, right? You see that the assembly code is pretty much copying the 2 in place, so there's no computation being performed. This gradient from Flux is actually pretty smart. It's intercepting this compilation, the Julia compiler, and doing very interesting things on the way. Now, the other advantage, which I think is the major one, is the fact that this gradient can be computed for arbitrary code, right? So if I say, for example, I have a program that takes some arguments x, y, and z, for example, and I start some r equals to x, I loop in some variable y in 1 to 10, for example, and I accumulate the value y, and I do some conditional check. If r is smaller than 10, I return r divided by z, otherwise I return r plus y times z, for example. So this is an arbitrary program. Think of any program that you could possibly write in Julia, right? Now I can ask Flux to do the gradient of this program at the parameters x, y, and z at given values. For example, I can say at x equals 1, y equals 1, I don't know, z equals 1, 2, or 3, let's say 2, 3. And what Flux will do, it will take this arbitrary program and you find the derivative. Even though there's for loops, there's if, else here in this ternary operator, it's able to find this actual derivative. I can actually check this. So if I say 1, 1 here, if you do 1, 1, you have x equals y, x equals 1, y equals 1. So you start r equals 2. You accumulate 10 times 1, so it's 2x plus 10y, and you have 2 plus 10, 12, so r is not smaller than 10, so it returns this part. And so you have 2x plus 10y here in the r, plus y, so you have 2x plus 10y plus y, so it's 2x plus 11y times z. So if I ask to calculate the gradient of 2x plus 11y times z, which is, let me write it here, so this is 2x plus 11y plus, and all this is multiplying z, if I didn't do anything incorrectly. You see that the gradient with respect to x is 2z, right? So if z is 3, 2 times 3 is 6. The gradient with respect to y is 11z, so 11 times 3 is 33. And the gradient with respect to z is 2x plus 11y, but x is 1 and y is 1, so you get 11 plus 2. 13. And so that's the least squares problem solved in two ways. First, with linear algebra, where you can see that the syntax matches the LaTeX syntax. And the second solution here with Flux with automatic differentiation, which is also an interesting solution to share. I hope that this clarifies the format of these notebooks that are upcoming. We'll be always having this initial setup of the problem, the geostatistical problem, in the next videos, and then we'll be solving this problem in different ways using the GeoStats project. I hope you enjoyed, and see you in the next video.